So good morning or good afternoon or good evening, everyone, and thank you for being here today. So today we have the pleasure to welcome Dr. Andrew Kiss from the Research School of Earth Sciences of the Australian National University. And today Andrew is going to talk to us about the computational modeling of the oceanic circulation and what these models needs to be able to work. So, Andrew, the floor is yours.
Yeah, thank you. So hi, everybody. So I'm going to talk about, it's a kind of an overview talk about how the ocean circulation, what the ocean circulation looks like, some of the important physics of it, and how we try to capture that computationally. And so this is work that, quite a bit of the work has been done by a consortium that I'm involved with for ocean and sea ice modeling. But just to step right back, put it into context. So we usually think about the oceans, or we often do, in terms of their role in the climate system. And so the Earth's climate system can be described as a heat engine. It's driven by variations in the incoming solar radiation with latitude. So more sunlight comes in near the equator, less at the poles. And that sets up density gradients, and that sets up circulation in the atmosphere, and also buoyancy forcing on the ocean, and wind stress on the ocean, and that drives ocean circulation as well. And so those circulations then redistribute the heat. So the Earth's surface temperature is much more uniform than you would expect just from the radiation coming in. So it's fundamentally a fluid dynamical system. You've got the fluid in the atmosphere and the fluid in the ocean, and the way they interact and behave. So just to fill you in on how the ocean circulation looks, this is a simulation. It's showing the sea surface current speed, and you can kind of see two different things going on here. There's a rapid flickering you can probably see, and that's a quite large scale. So just play it again. And then there's much finer scales that are moving more slowly. So there's kind of two things going on here. This is the surface current, and the surface of the ocean is being pushed around in a thin layer by the winds, and that's being reflected in those large scale patterns. But also that only extends about tens of meters deep. And then the rest of the pattern you can see, the finer scale pattern, is much deeper currents, which are being pushed around ultimately by the wind, but through some quite complicated processes. So you can see there are intense currents on the western sides of the ocean. So there's one off Japan called the Kuroshio current, one off the side of the US called the Gulf Stream, one off South Africa, that's the Agulhas current, and so on. So each of these western coasts, each of the western boundaries of the oceans, the eastern coasts, has a boundary current. There is also a major current around the Antarctic, called the Antarctic Circumpolar Current, which is one of the most important currents in the world. So these are the sort of surface horizontal circulations of the ocean, and these extend, in most cases, a few hundred, maybe a kilometer deep. But there's also, and they're primarily horizontal, but there's also some overturning circulation. And you may have heard of the global ocean conveyor belt, but you may not have seen it depicted like this. This is called the Spillhouse projection. This is a favorite among oceanographers because it chops up the continents and leaves the global ocean as one big piece. But you can see there's Antarctica in here, there's Africa, there's the Atlantic, and so on. So there are just a few places on Earth where there's intense cooling and/or salinification of the surface of the ocean, which makes the surface waters dense, and then they sink to the bottom of the ocean. And so those dense waters will spread out from those few locations, and they actually fill up the oceans from below. And so most of the volume of the ocean is actually very cold water, which originated from polar regions, and it's actually spread throughout all latitudes and gradually diffuses upwards. So that sets the properties of much of the water in the oceans. So here's just showing you where the water is formed around the Antarctic. This left-hand plot is actually a plot of the concentration of a chlorofluorocarbon, which you can use to track where the water gets to after it sinks, because that hasn't been in the environment for too many decades. So you can see how far the water's gotten. And then this is a computational model, which shows in red the places where the surface water is being cooled and made more dense and sinking. And then the green stuff is basically water that's been at the surface recently and is spread out across the bottom. Just to give you some more visualizations. So this is, whoop, turn off the sound. So this is the Antarctic, and we're going to zoom in and peel away the surface of the ocean. All right, so these are the surface currents, and this is peeling away and looking down in the ocean at a particular density level. So one of the important things about the ocean is it's stratified, which means there's dense water lying below less dense water. So as you go upwards in the water column from the bottom, the water gets less and less dense. And if you pick a particular layer at a particular density, that's called an isopycnal. And these are this is one particular isopycnal in the ocean. So water below this surface is denser, and water above it, which you can't see, is less dense. And what we're going to see is, as we come into the coast of Antarctica, this is the Antarctic Peninsula, and I'll just speed it up a bit. Oh. You get this region here. So this is a place where the ocean is being cooled and become more dense due to sea ice formation, and you get sinking. And there's another spot over here in the Ross Sea, again peeling back the surface layers, and you can see the dense water basically running down the continental slope like a huge waterfall in 3 particular canyons. So this is the dense water that's cooled on the continental shelf, runs down these canyons and fills up the ocean from below. And we're actually capturing this in a computer model. And I'll just run this forward a bit further. So again, you can see these different layers of different densities. So that's it's 1,037.04, 1,036.89. So very small density differences, but they're actually really important because the oceans aren't energetic enough to be able to mix those away in most places. So they're barriers to circulation. And here we are. This is South Africa. This is the Agulhas Current, and it folds back on itself and breaks off into these big eddies. So these are called mesoscale eddies. And you can also see the Antarctic Circumpolar Current. There's lots and lots of eddy motion going on there. So that's a quick overview of what the oceans are like. Now, so the role in the climate system. So the oceans are a really fundamental and really important part of the Earth's climate system. As I've said, they transport heat from the equator to the poles. Which the atmosphere also does. They also store about a quarter of the CO2 that we've emitted, and they store about 90% of the excess heat because of that. So it's pretty fundamental to the climate system. So if you're going to make a climate model, you need an ocean representation. And the way climate models work is they're actually have separate codes for different components of the models. And that's basically a historic thing. Different people specialize in the ocean or the atmosphere or the sea ice, and they've written codes, and then they've worked out ways to couple them together. So this is a sort of schematic showing how the ocean, sea ice, the biogeochemistry in the ocean, the atmosphere and the land surface and atmospheric chemistry and so on are all connected together and into a coupled climate model. And there's the ocean. So there are so this is an example of a simplified model which just looks at the ocean and the sea ice. So this is one that I've worked on for a number of years now. And so we have a sea ice model called SICE, and we have an ocean model called MOM5. And you can see that there are different things being transferred between those models to communicate with one another. So, for example, when the sea ice melts or freezes, it transfers things like salt and water between the ice and the ocean. And there's also, there's heat transfers and so forth. And this is all driven, this is actually not a complete climate model. This is just ocean and sea ice driven by a prescribed atmosphere. So we have a realistic prescribed surface forcing. So there are a lot of models that are set up like this, where you can look at some of those climate model components in isolation, and that way you can do more, you can afford to do higher resolution experiments or look at particular features in more detail. People also do this with the atmosphere, where they have atmosphere-only simulations. But if you're going to do the whole climate system, it's necessary to have active climate components as well. So this is another model that I've been involved with. So this again has an ocean model, a sea ice model, and now we have an active atmospheric model. So it's a dynamic atmosphere driving the whole thing through a coupling, through a coupler. All right, so just to bring it back to some physics. So the governing equations for fluid motion are what's called the Navier-Stokes equations. And this is basically the momentum equation. This is the Newton's equations of motions written out in a form that's suitable for a fluid. So what you have on the left here is acceleration, and what you have on the right is forces, roughly speaking. Now what we've actually got here is, so that's the velocity, u. This omega here is the Earth's rotation vector, so that points upwards out of the Earth's North Pole, if you like. P is the pressure, rho is the water, is the density of the fluid. G is the acceleration due to gravity, and we're using kind of vector calculus sort of notation here. So this is acceleration, but it's being divided through by density. So that's why the rho's on this side. Now, we're all very familiar with fluids. Every time you have a cup of tea or have a shower or get on a bike or whatever, you're dealing with fluid dynamics. And the flows that we're familiar with in everyday life are dominated by particular terms in this set of equations. So flow around a car or a cyclist is dominated by the acceleration and advection terms and the pressure gradient. And so you can see the pressure distribution on the front of this cyclist here. And in other situations, so if you're pouring honey, you might have a flow which is dominated by pressure gradient and viscosity, for example. Whereas the situation on the Earth with the atmosphere and the ocean is actually very different. So we've got this different term that we basically never experience in everyday life called the Coriolis term. So that acts at 90 degrees to the velocity. So in the southern hemisphere, it turns things to the left. In the northern hemisphere, it turns things to the right. So that's fundamentally important for large-scale atmosphere and ocean circulation. And there's also gravity, which is very important. And there's also the fact that it's on a sphere, which is important. So a lot of the intuitions we might have about fluids actually don't apply when you talk about the atmosphere and the ocean. So, if we think about computational fluid dynamics for the ocean, these are the kind of ways you might specify it as a computational fluid dynamic problem. You've got a thin layer of fluid, it's stratified, so it's dense at the bottom and less dense at the top, and it's on a rotating sphere, all right? Now, when I say it's thin, so the oceans are something like 4 kilometers deep on average, and a typical ocean basin might be maybe 5,000 kilometers across. So you've got about 1,000-fold difference in thickness to width. And that's actually a similar aspect ratio to a sheet of paper. So the thickness of a sheet of paper compared to its width. So that's a really quite extreme aspect ratio. So the movie I showed with the cross-section was really exaggerated and vertical, so you could actually see what was going on in there. There's the stratification, which I showed you in that movie. And this is really important because it restricts the motion of the water. So the water moves very freely along a layer of constant density. an isopycnal layer, and it mixes freely along that layer, but it can't move or mix very easily across those layers. And that's because that involves potential energy. So when you lift up something dense and displace something light, you actually have to do work against gravity. So the energetics of that restrict the mixing and the motion across the isopycnal layers. What it also means is because it's thin and the ocean currents are nearly horizontal, the Coriolis force is actually mostly acts on the horizontal velocity. So with the stratification, that actually governs the vertical momentum equation. And so the balance there is very, very close to being hydrostatic. So the vertical pressure gradient's balanced by gravity, and I'll show you that in a formula in a moment. And in the horizontal, we've got the Coriolis force, and that is, as I've said, dominant. And what it does is it's balanced primarily by the pressure gradient force. And you might have seen this on weather maps. So you're probably used to looking at the isobars, so the pressure contours on a weather map. Now, in a non-rotating flow will move across pressure contours, so it'll just slump outwards. But you don't see that in a weather map. The wind actually follows the isobars. It goes around and round. And that's because the Coriolis force, which is at 90 degrees to the velocity, is balancing the pressure gradient force. So very different dynamics. And that Coriolis force also depends on latitude. So it's strongest at the poles, which is also important. So all of these things are kind of unique to these sorts of flows. And they're very different from what you have in, say, computational fluid dynamics, like the pictures I showed of the flow around a car and a bicycle. Basically, different terms in the equations are of leading order importance. And also different things are important to get right. So in the ocean, we really care about minimizing spurious numerical effects, in particular spurious numerical diffusion of heat and salt. Because in the ocean, when water sinks, say in the polar regions, it goes down into the ocean, it actually maintains almost exactly the same temperature and salinity as it moves along those isopycnal surfaces, and you can use that to track where the water has gone. So we can't use ordinary computational fluid dynamics codes to study these flows. So we have ocean models. So these are specialized CFD codes, and they're engineered often just for the ocean or just for the atmosphere, although there are codes which work for both, and they obviously change the density and change the equations of state and so on for the different fluids. So they're useful for climate modeling. They're useful for forecasting where eddies might be in the ocean, working out where marine heat waves are going to happen or what causes them, and this sort of thing. So here's a movie. This is going around the Earth, and you're seeing here all the eddies that are showing up in the ocean. So this model is what's called an eddy resolving model. So it can resolve the largest of the eddies in the ocean. So this model is actually quite similar in a lot of ways to a weather forecasting model, but it's been set up to deal with the ocean in particular. I'll just quickly mention we also have models for the sea ice, and they're also different and they're specialized. And this time we're talking about frozen seawater, so the different from icebergs. So the sea ice is just frozen seawater, and this is modeled usually as a bulk viscoplastic fluid. So you can't resolve individual flows normally, and you represent it as a viscoplastic fluid, which actually seems to be quite a good representation of large-scale sea ice motion. So climate models usually have an ocean model and a sea ice model coupled together in this way. Okay, so if we want to model the ocean, we have to think about the length scales that are important in the ocean. There are a huge range of scales, and so there are, for example, convection and things that might happen at, say, 100-meter scales. There are sub-mesoscale and mesoscale motions, so-called. So the eddies we saw are around 10 to 100-kilometer sort of scales. Then there's sort of large-scale currents. That's the California current. Then you've got basin scale things like El Nino and so on. So there's an enormous range of scales of motion that occur in the ocean. And just to show you how it differs from the atmosphere, So this is a plot which is showing you atmospheric circulation with the streak lines. So the little white lines that you can see there, they are showing flow going around low and high pressure systems in the atmosphere. And then the colors are showing you circulation in the ocean. So that's the current speed. And these structures are actually dynamically equivalent in a lot of ways. So these high and low pressure systems in the atmosphere are equivalent to these little eddies in the ocean, but they're at a very, very different scale. Okay. So there's something like an order of magnitude different in scale. Um, and and there's actually a dynamical reason for that. So the reason we even have these eddies is that these fluid flows are actually unstable. And there's a range of different instabilities, but one of the most important ones is called baroclinic instability. And this has a characteristic length scale, which you can write down like this. So F here is the Coriolis term, which is related to the Earth's rotation rate and the latitude. And delta rho on rho is the stratification. And it turns out when you plug the numbers into this, you get thousands of kilometers for the atmosphere and tens to hundreds of kilometers in the ocean. And so to represent these little tiny things in the ocean, you need much higher model resolution. So the computational model needs to be higher resolution, and that actually makes it more expensive in that regard than modeling the atmosphere. It's a more difficult task in that way. All right, so we've got the equations of motion and we want to try and represent them on a computer. So what we do is discretize the equations. So what we do is we break up the world into little boxes. So this is the real world on the left. This is a discretized version on the right, and it's just like pixelating an image, except that we do it in 3 dimensions. So there's a stack of boxes in the vertical as well. So it's a 3-dimensional pixelization of the ocean. And we get our equations of motion. So this is the Navier-Stokes equations again, but this time I've written it all out in components, and we first of all make some approximations that are good approximations to the ocean. So we cross out almost all the terms in the vertical and are just left with the pressure gradient balancing gravity. So this is the hydrostatic equation that I mentioned previously. And these two are the 2 horizontal components, and in ocean modeling, we need to keep basically all of those terms, although one of the Coriolis terms is normally dropped. Oh no, that one's kept. Sorry. No, they're all kept in there. Yeah, and so what we do is we break up into these boxes, and then we look at the differences from one box to the next. And so we look at, for example, the pressure difference between 2 boxes and divide it by the distance between them, and that's this equation here. And that gives us an approximation to the gradient of the pressure. And so that becomes a forcing term in the equations of motion. So each of these terms can be written in terms of differences on a grid. And what I've written here is highly simplified. In practice, much more sophisticated methods are used, but this kind of gives you the idea. So each grid cell has an index, and you go to the next index to the left and the right, or north and south or whatever, and take these differences for these terms. So that sounds straightforward. But there's actually a difficulty that when you put things on a grid like that, you can actually get a system which behaves extremely differently from what you expect. So if things work well, it gives you realistic results. But if you choose your parameters wrong, you can actually get complete garbage. And one of the ways to get the parameters wrong is to break what's called the CFL stability condition. And what that means is that when we step these equations forward in time, we have to take a time step that is shorter than the time it takes the fastest wave or current to cross the smallest grid cell. Okay, so when grid cells get small, or when wave or current motions are fast, we need to have a short time step. And a short time step means you'd have to take lots and lots of short time steps to simulate a month or a year or 100 years or whatever it might be. And that makes it much more expensive. So when we want to go to high resolution, you have to have much more data. So for example, if you're doubling the resolution in the in the horizontal in both directions, then that's 4 times as much data, but you've made the cells half the size. So you need to make the time step half as long, right? So then you've basically lost an order of magnitude in computational speed. So very quickly gets out of hand. Now, the fastest speed in the ocean, other than sound waves, which we already neglect, is the surface gravity wave speed. So these are just the waves you see on the beach, except in the deep ocean, they travel really quickly. So this is the speed that tsunamis travel at, 200 meters a second. This requires a really short time step, so maybe 10 seconds. So we might only be interested in what happens on a day or a month kind of time scale, but we actually have to resolve the ocean in really short increments. But there are methods, which I'll show in a moment, to get around that. Also, we don't want our grid cells to get very small. And so if we have a grid which just is latitude and longitude, obviously it goes to 0 spacing at the North Pole, which is a problem. So we use these unusual kind of grids, which actually have 2 poles in the north, and we put them on land because we don't need to simulate the land. And then we don't have any singularities in the ocean. So there's a whole lot of different tricks to get around this condition. Yeah, I'll just skip that one. So this is an example of a split time stepping scheme. So we can actually split the equations of motion into a depth independent part, which is 2-dimensional. So this is the depth averaged current and depth average pressure gradient. And then there's the 3-dimensional stuff, which is obviously more expensive to do because you're calculating in 3 dimensions. And you can split the equations so that you can solve the 2-dimensional part separately. And the 2-dimensional part is the part in which the surface gravity waves live. So these are the fast waves that require a short time step. So basically, we're going to have a short time step with a cheaper set of equations. And then the expensive equations we can actually run at a longer time step. So that's what this diagram is trying to show. You've got a main loop here, which does the 3D time step round and round. And within each 3D time step, you have maybe 100 2-dimensional time steps. And that will speed your model up by a large factor. Even so, it's very hard to get high resolution in climate models. So these are 3 models, or 3 different resolutions of the same model. So the left-hand one here has got a resolution of around 100 kilometers, and that's actually typical of climate models. Then there's what's called eddy permitting ones, and this is about 25 kilometers resolution. It can just begin to resolve those eddies we saw in the ocean. And then you can get an eddy-rich simulation when you get down to around a 10-kilometer. The trouble is, it costs hundreds of times to 1,000 times more expensive to do this than that. So climate models actually tend to be at this extreme or maybe in the middle. So just to show you this is a similar problem in the atmosphere. This is just showing you, this is quite old here, but this is 1990, 1996, and so on up to 2007. With atmospheric and land surface models in climate models, and you can see you gradually get a more realistic looking picture of Europe. So to do these things at scale, you actually need a supercomputer, and this is really just thousands and thousands of pretty ordinary computers connected together with a very fast network. So some of the simulations I've shown have used hundreds of millions of grid cells and tens of millions of time steps and thousands of computational cores, tens of thousands. And even so, using a high-performance supercomputer, it may take months to run. So these are very, very big undertakings to do at high resolution. I'll just show you what happens when you do go to high resolution. So this is something like a 5-kilometer resolution. This is showing the rotation rate of the water. It's called the relative vorticity. And if we go then to higher resolution, Now we've got a little section in the middle here where we've made the resolution 4 times higher in each direction. And you can see we've got very, very fine scales emerging that were just not possible to resolve in this other coarser resolution. And the behavior's becoming much more complicated. So this is geophysical turbulence. This is the turbulence that you get in the ocean. Now, I just want to quickly touch on that because it's one of the key difficulties with ocean modeling. So turbulence happens essentially when you've got instabilities that feed on themselves at different scales. So this is one example of a turbulent cascade, I suppose. So this is what's called a Kelvin-Helmholtz instability. We've got 2 layers of fluid and the bottom layer is moving to the left and the top layer is moving to the right, and that causes shear, and that shear rolls up, and you can see how it rolls into these large vortices. Each of those then rolls up into smaller vortices, and each of those rolls up again. So this is zooming in and zooming in and zooming in. So this is just a neat example of how eddies can feed on eddies, and this is recognized by Lewis Fryer Richardson, who was one of the first people to envisage computational atmospheric modeling. So the trouble with the ocean is this turbulence actually extends from scales of hundreds of kilometers down to a few centimeters, and we can't possibly hope to resolve all of those scales. So one of the big things that is worked on in the theory of ocean circulation and modeling is how do you deal with representing the turbulence that you can't resolve on the computational grid. And there's lots of ways of doing it, and some are better than others. So just to show you what turbulence looks like. So this is a 2-dimensional simulation. And so it's quite similar to how the ocean works, because the ocean is primarily 2-dimensional. And we've got several things going on here. So in the middle is just showing you the way the water moves with some colored floats. So there's thousands of little floats in the water that are moving around. And the one on the left is the vorticity. So this is the rotation rate. It tells you whether it's rotating left or right and how quickly. And the one on the right is what's called a wave number spectrum. Okay, so the wave number is the inverse length scale of this circulation. Okay, so it's the inverse of the wavelength, if you like. So if you take a Fourier spectrum of this, it looks like this right-hand picture. So this far right end here is the fine scales, and the far left end is the coarse scales. And this is a simulation where there is forcing added in these intermediate scales. And what ends up happening, and I'll just go back to the start. You can see the energy is just in the middle to begin with, and then it spills out both to finer scales and to coarser scales. And the way this happens is actually, again, different from what is familiar from everyday life. Because this is 2-dimensional, you actually get energy moving up scale, which is just something that doesn't happen in normal 3-dimensional turbulence. Like if you're stirring a cup of coffee, you don't end up generating eddies that are much bigger than the scale that you force at. So that's another way in which ocean and atmospheric circulations are very different. Okay, so I think I'm close to time. So I might just leave it there. So in summary, oceans are a crucial part of the climate system, and the way that they behave is very different from the flows you might be more familiar with. And because of that, you require specialized computational codes to represent them efficiently and accurately. And this also requires really quite large computational resources if you're doing it at high resolution. So I'll just leave it there and take questions.
Well, thank you very much, Andrew. It was a very good talk. So are there any questions in the room? Or anyone have question? You can unmute yourself and ask a question, or you can put it in the chat.
Yeah, we have one question from Emmanuel.
Yes?
Yeah, Emmanuel, you can just walk here and then.
Yeah, maybe Emmanuel, come forward.
There was a part on the slide where you carried out the.
Sorry, the sound has just dropped out.
Yeah. I think they are frozen.
Yeah.
Mm. Maybe let me ask to put it in the chat. Or
Okay. I think I'll need to end the show to look at the chat.
they came out. I think they will come back. So, anyone else having a question? I have some, but I'm waiting for the students to come back.
Okay, sorry, we had a technical problem. I'm sorry.
No problem.
Yeah. Emmanuel, can you come and ask your question again? I think Emmanuel was asking about the discretization of the domain on which you place the grade. So if you can go back to that slide where you had the discretization of the finite element, finite difference.
So yes, I wanted to ask, why did you use the second order centered finite difference in your approximation?
Oh yeah, good question. This is not it's not a fair representation of the way it's usually done. This is an example to make it clearer. There are all sorts of different methods that are used. So there are different methods that are used in different models. But typically, often they are second order methods in space in these sorts of models. One of the reasons for that is as you go to higher order methods, you need a larger stencil. So you need more points further away from the point you're trying to calculate. And that ends up, because we do this in parallel, we break up the ocean into pieces, and each of those needs a halo. So it needs grid cells that overlap with the neighboring panel or the neighboring tile. And as you increase the size of the stencil, the halos get bigger, and so that can make it computationally less efficient. Another thing is that ocean models actually don't use finite difference per se. They tend to use finite volume methods. And the reason for that is that there's important conservation properties that are important to get right with finite volume. So that so conserving volume, conserving salt, conserving heat, things like that. And and finite volume methods tend to work better for that.
All right, thank you.
Right, good question.
Well, Andrew, actually, I have a question on this slide. So I understand that we neglect the vertical velocity, but could you explain why you still have to keep all gradients of each component velocity, horizontal velocity in the other two equations?
In these ones?
Yes, on these ones. Why do we, is there, why do we keep all the partial derivative of du dx, du dz, and du dy, and same for v? There is no way we can simplify some terms like we do in
Yeah.
Newton.
Well, it would be nice, but no, not in fact. The So I mentioned that the dominant balance is between Coriolis and pressure gradient.
Mm.
But the trouble with that is that it doesn't involve a time derivative. So there's no evolution in that, right? So that's called the geostrophic balance. From just geostrophy, you can't actually calculate how things will change with time. So although that is, dominates the balance, you actually need to include other terms in order to handle it, in order to actually have the time dependence. And yeah, so in practice, these things are included. The advection term, for example, is not so important on very large scales in the ocean, and so it's often not dominant in very low resolution models. But when you get to high resolution, that becomes a really important term in those eddies, for example. And one measure for that actually is, so F here is the Coriolis parameter, and then you can work out the relative vorticity of the flow. And if the relative vorticity of the flow becomes similar to the vorticity of the Earth, you start having to worry about the advection term. The viscosity term, I've put this in here. This is kind of rough. What I'm doing here is, so I mentioned there's turbulence, and it can extract energy at fine scales, and we need to do that in a numerical model, because otherwise energy can build up at the grid scale and cause instabilities. But we can't resolve the molecular viscosity, the scales related to molecular viscosity, because those are like centimeters. So a very crude trick to get around this is to just increase the viscosity. And so that's called an eddy viscosity. So that's a parameterization for the eddy, for the turbulence. Yeah, there's often more sophisticated schemes than that, than what I've written here to deal with that. So yeah, so I should have made it more clear that this is not molecular viscosity we're putting in here.
Okay, thank you.
And actually, I should have also said a lot of this stuff. I mentioned that motion is much easier in parallel to the isopycnal surfaces than across them, and so you tend to need to have schemes which can give you greater effective eddy diffusivity in that direction than across it. And so there's some fancy ways of going about doing that.
So I'll have other question, but there is a question in the chat from one of our students. Thank you much, sir. So what are the main sources of uncertainty in your model, and how do you deal with them? And question 2, how do you validate your model outputs, especially in data sparse regions like a deep ocean or polar area?
Yeah, they're excellent questions. So I guess I'll start with the validation. Yes, a lot of the ocean is very sparsely measured, and the surface ocean is much better measured. You've got measurements of temperature and of sea surface height, for example, which are really really useful, and they can be compared with what the ocean model is generating. We also have in situ measurements of particular currents in particular places. So we've got some measurements of overturning in a few places, and measurements of particular boundary currents and things like that. So they can be kind of directly compared. But there is a great deal which can't be validated in any direct way. And yeah, we make the best use we can of what information we have available. There is one thing I should have mentioned, perhaps, was that you saw all these eddies and all this turbulence. So this is a chaotic flow, and so because it's chaotic, no matter how good the model is and no matter how good the initial conditions are, the eddies are not going to be in the right place at the right time compared to reality. But there are methods to fix that, which are called data assimilating methods, where you take as much data as you can, observational data, and you feed it into the model in real time. And so this is what's done with ocean forecasting and also with weather forecasting. And so you can actually continuously correct the model to keep it close to reality. And so you've got something which is a bit of a hybrid between a free running model and an observational data set. It's a model which is sort of being pushed towards data. Uncertainties in the model. So there's uncertainties in terms of there's some kind of known problems. So one of the known problems is the numerical methods that we use. They have all sorts of, like, all numerical methods have problems of one sort or another. We choose methods that are kind of good enough and are computationally cheap enough that we can afford to run them. But one of the issues is unwanted mixing between different isopycnal layers. And that can blur out the distinction between water masses and cause all sorts of problems. So over the decades, people have come up with more sophisticated ways of handling this. One way that that's done is, instead of using a static computational grid, we have a grid which is static horizontally, but moves vertically with the isopycnal layers. So that because the grid moves with the layers, you don't get computational sort of mixing of properties from one layer to the other. So it's called an isopycnal coordinate layer, a coordinate model. And then there are, but that has problems of its own as well. So yeah, there's always uncertainties with these things. And we can be uncertain about the uncertainties because the observations are sparse. But we do what we can to validate things, and it's not that uncommon for us to discover something in the model and then look for it observationally and find out that it actually existed, which is kind of nice. So, for example, there are some of the dynamics of the flows down the slopes around Antarctica have been predicted from the models and shown to exist in reality. And I guess I should say that, we don't tell the model to put any of these currents where they are. So the Gulf Stream or the Antarctic Circumpolar Current, none of those things are prescribed. They just come out of the dynamics. So if you've got the right dynamics and the right forcing, you can end up with currents in the right places.
Okay. Thank you. Thank you. Anyone else has a question? Sylvain, you have a question?
I think you just said.
Yeah.
Okay, thank you for the nice presentation. Okay. Now, my question is related to the influence of earthquake to the dynamic of ocean. Now, in your calculation, how do you recognize the influence of earthquake to the dynamic of ocean?
So the influence of what? I didn't catch that word.
Earthquakes.
Earthquakes.
Yeah.
Oh, right. Yeah, there are. So you're thinking about tsunamis?
Yes.
Yes.
Yeah, so there are models of this sort that are used for tsunami modeling. Tsunamis are a surface wave, and because of that, you can actually get away with a much cheaper model. So, so there are specialized models that are used for tsunami forecasting. And so because it's a surface wave, you don't actually need to worry about anything happening in 3 dimensions. You can just have the depth integrated or depth averaged velocity and the sea surface height, and those are the only things you need. So there's 2 components of velocity and one surface height or pressure. And so that's actually a much cheaper calculation. So it's just kind of this part, and you can skip all of this part. So because of that, the tsunami models can be run at much higher resolution, which turns out to be important because when tsunamis approach a coastline, there are all sorts of effects that happen so that the waves will start to refract when they hit shallow water, which can concentrate the energy in particular places and these sorts of things. When it comes to tsunami inundation, that's actually a really difficult problem because then the boundary of the ocean is changing because it's spreading out to the land. So you need more sophisticated modeling techniques to have to allow that to happen. And so there are specialized models which are not done for the scale of an ocean basin, which you might have for a tsunami propagation. For the tsunami impact, you might have a specialized model that's run in a regional area, which can deal with the inundation, so the moving coastline, and even deal with flow around buildings and small scale obstacles like that.
Thank you.
Okay, okay, thank you. Maybe I'll ask a quick one on the, you mentioned the model simulations, okay? What about the model analysis and the amount of data you generate? How do you analyze all these models, all this
Right.
modeling data?
I've probably got some slides on that down the bottom of this. It's a big problem actually. So because we've got hundreds of terabytes of data, you don't want to download that onto your local computer because you can't, right?
Yeah.
So the analysis also runs on the supercomputer. So the data analysis we do uses the supercomputer. So the principle here is you move the computation to the data rather than moving the data to the computation. And the methods we use, well, we do our analyses in Python, and there are some packages in Python that make it reasonably possible to do. So there's a package called Xarray, which can represent the files in a usable way, and a package called Dask, which allows you to use multiple cores at once to analyze the data. And so you can do the analysis in parallel as well. So you might have like 64 cores running to analyze these big data sets. And the other thing we do is we have databases for our experiments. So all the experiments might generate many, maybe 100,000 files. And nobody wants to plow through all of that. So we have a database that lets you just say, I want, the temperature and over this time period or whatever, and it goes and finds the right files for you and makes it accessible.
Okay.
But that's actually, it's a really important thing to get right if you actually want to do something with the data.
Yeah, I was thinking that it was it's also administered by NCI.
Yeah.
Yeah.
Well, yeah, and it's so it's all stored on NCI. But we have a big consortium where we cooperate with the runs because they're so expensive. So we'll save outputs that multiple people want to use, and we share all the data freely. So anyone can get a hold of it and do things, and so we've got a whole communities that sort of spring up around these data sets to write papers on different things, and there's so much there that lots and lots of people can work on different parts of the ocean simulation without treading on toes.
Okay. Well, impressive. Okay. Well, I think we'll close it here. And thank you very much, Andrew, for your presentation. I think it was very interesting for our students. So thank you very much for joining us all the way from Australia.
No, thanks for your attention. It's been a pleasure.
Yeah.
So, yeah.
Okay.
Thanks for the opportunity.
Yeah.